Mailboxes and synchronization. So what is a mailbox? So now we can start, now that we have a semaphore, we can start to create other more sophisticated things, because remember, a semaphore is just a flag. Okay, it's a protected flag. It's a special flag. And a mailbox is, all that is it's a memory location with a key. And so again, this is going to be something that is protected by a semaphore. And so we give it, it's therefore maintained by the operating system, so that the operating system can put tasks to sleep and wake them back up again using suspend and resume, so we don't have spin locks wasting CPU execution resources. And the basic functions associated with a mailbox is a post and pend. Okay, so post writes to the mailbox location and pend reads from it. And again, we simply use a semaphore to guarantee that two tasks aren't trying to write at to the same location. So again, it allows these post and pend operations. If there's no key in the mailbox, then the task is going to have to block. And so there's either an accept or a check operation to just see if the key is available, for example. And that's, you can, in other words, that's kind of like a flag on a mailbox. The postmaster doesn't have to stop and look for for if there's no mail in the mailbox, right? And so using mailbox interrupts again can force this, so there's no spin locks or busy, what's called also called busy waiting. And then of course you can also have mailbox queues. You can have a series instead of just a single known memory location. You might have a queue, some sort of first in, first out queue or whatever, so you can have pending requests. Again, this is just functionality built through synchronization that also provides communication. Okay, so it's data that's protected and synchronized so that two tasks are not writing over the same variable. Again, this is very important to maintain accurate communication, right? Is we have to synchronize multiple tasks trying to use the same communication pathway. Now, there are a number of things we can use. There are global variables, which we've seen. We talked about how we could use a global variable to implement our software hack for a flag, for a waiting flag. But again, global variables aren't protected. And so you need something better than global variables. One of the things we use, particularly when we have strings of data, in other words, data structures, that take time to, there are multiple instructions to write, and so they're more likely to have a collision. A double buffer is just a pair of buffers, and you talk to it as a single one, and it allows one task to be filling one of the buffers while a different task is draining the opposite buffer. And so double buffers is a good scheme when, again, you have to have time correlated data. Say, for example, a vector of joint variables from a robot, right? If it has 6 joints, you don't want those, 3 of the joints to be read from one time step and the other 3 to be read from another time step, right? Or to be overwritten so that it corrupts the integrity of the snapshot. And so that's a way to use double buffers. Now, triple buffers is another case that you might want to implement. Now, you can imagine, well, hold on, why would I do that? Okay, imagine the case of a double buffer, right? What you're doing is you have multiple tasks that are reading and writing data. So one task might be reading the robot's joint variables to understand, to compute the forward kinematics of the robot, for example. And while another task is going to be writing that variable, right? And it's going to be, say, a PD controller or something that's reading the sensor values. And so what you can do is if you have these two buffers, right, the reader can point to the one variable and it'll say, okay, I want to read the variable now, while the writer is pointing to the opposite pointer, the opposite variable. In this case, of course, it's a vector of variables. And then with those two, one can be reading while the other is writing. And then you flip-flop. When the one is done reading, you say, okay, well, where's the most recent? Then you look, has the other vector been updated more frequently? Well, then you flip-flop the pointers so that now on the next read cycle, it gets the updated value. Okay, and see, that's how you can protect the two. Triple buffers, however, might be in handy where, okay, imagine that the reader and the writer are working at different speeds. So the reader may be reading from buffer A. Of the three buffers, we're going to have A, B, and C. So the reader is pointing to A. The writer is pointing to B. If we have only two buffers, then if the writer is still writing to, is not done writing to B, say it writes a value into B, but A is slower, and it is still reading from A. Well, then B is going to say, oh, if B comes back and it's time to write, then it's going to be still pointing to B. And so it's going to say, oh, okay, I'm going to update B again. Well, if then task A comes back, it's still pointing to buffer A. And so it's actually going to get an old copy because the latest value B wrote into it now is being overwritten. And so it's protected. And then you lose that piece of data because of the time it takes to finish reading and writing. Okay, so triple buffer mechanism is a way to prevent that. Imagine you have buffers A, B, and C. So the reader is looking at A. The writer starts to fill B. Okay, now it finishes filling B, but the reader is still looking at A. Okay, so the writer goes to sleep and it wakes up again. It's already filled B, and now it can start to fill C and say, oh, I'm going to start filling up C with the latest data. Now it's not done with C, but it has updated the value of B the last time. So when the reader then goes to sleep and wakes back up, it can say, oh, I've already looked at C, or I've already looked at A. C is in use, so I can look at B, and that'll give me the most recent value. So you eliminate that if the writer is operating at a higher frequency than the reader. You can prevent loss of data with a triple buffer system. Okay, now another type of communication mechanism is the ring buffer, okay, or circular queue, where you can put data in and then you just circulate around to what the most recent is. And again, this is another way that if you and it's very similar now to triple buffers, only it goes to 4, 5, or 6. You put that in a ring, and the writer can be pumping data in one end of the ring, and then the reader can it can choose to skip over some of the older ones and go to the most frequent or the most recent fully written value. Okay. Now, message passing, we're going to set up queues for different message packets. And now again, a packet is a protected and self-coherent data structure. And typically for that, we're going to use mailboxes because then we can set up these protected, semaphore-protected mailboxes that can have arbitrarily sized data structures. It could be any number of these queues or these, types of structures where they're double buffers, triple buffers, multi-buffers, ring buffers. And this way, we can ensure secure point-to-point communication that is either one-to-one, one-to-many, or in fact many-to-one. Unix style sockets are implemented usually across most operating systems. So that's become just like semaphores are kind of the default synchronization mechanism. Sockets are a packet-based secure communication mechanism. They have fairly high overhead because they do ensure for message transmission and retransmission when necessary, but they're high performance kind of communication functions. Okay. Now, I want to point out some things about Kimera because it had some novel features even in today's, this is a very old system, but it illustrates a lot of the interesting capabilities. And Kimera actually implemented a protected form of global variables. And this was interesting because it's provably optimum communication. There's minimum overhead and still maintaining protection of global variables, but they do act as global variables. They're one indirection away, I'm sorry, from global variables. And basically the microprocessor, and this was even across a multi-processor operating system, so there could have been multiple independent processors running the OS that could share these global state variables and give you extremely fast communication performance by basically sharing pointers to each other's memory, but again, it was protected. And there's only operational overhead was during initialization, so there's no runtime penalty, and provides this one-to-one and one-to-many. And it did not, the global variable scheme did not allow directly for many-to-one, but then an implementation was created for what's called a join connector.